In this video, we're going to talk about chapter 12, and it's the last of our lectures. And this chapter deals with an introduction to organic compounds. Okay, so organic compounds are mostly carbon and hydrogen type of compounds. So um, uh, one part of the compounds are called as hydrocarbons, all right? And we'd already encountered them like butane and methane and propane, okay? And sometimes there are other elements as well in organic compounds. The source was thought to be um, uh, living things. That's hence the name organic. However, you can manufacture most of these organic compounds in the lab, all right? So you can even manufacture some of them like urea from inorganic sources, all right? So the topics we're going to deal with are in the first introduction to organic compounds, what they are, and then one set of organic compounds that we're going to be just emphasizing are the hydrocarbons, the carbon hydrogen compounds. Among them, the alkenes, right? So we'll spend most of the time 12.2, 12.3, and 12.4 talking about alkanes, okay? Different kinds of alkanes. Um, Alkanes with and without the substituents, all right, the branches, and then the properties, some of which you already know, a few like fuel, all right, octane, okay, a kind of alkane. If you burn it, you produce carbon dioxide and water, all right. So the hydrocarbons, if you burn it in the presence of oxygen, produces carbon dioxide and water. This we know, burning of propane or any kind of carbon compound is referred to as combustion, okay? And then we look at another group within the hydrocarbons called as alkenes. The ene stands for double bond. So these are double bonded hydrocarbons, and then alkynes, which have triple bonds, all right? So triple covalent bonds. These are triple covalent bonded hydrocarbons. And then this a phenomena called as cis trans isomer, but we won't it's mostly found in the double bonded um, hydrocarbons, the alkenes, but we're not going to emphasize too much on that. And then this last part is the most important part, the functional groups. So there's so much, millions of organic compounds. It's impossible to study each and every one of them individually. But if you group them into these groups called as functional groups, all right, that means taking those carbon compounds, organic compounds that have something in common, all right, and then when you make those common groups and you categorize them, then it's easy to study the compounds based on their functional group, because each compound within that group acts very similarly, all right? So this part, an introduction to the functional group and how to recognize them, is what we are going to put a lot of emphasis on, all right? Okay, so I mentioned the word hydrocarbons. That means there's two elements, hydrogen and carbon, all right? So basically, organic chemistry is the chemistry of carbon, especially the hydrocarbon, okay? All right, so here you're seeing some medical emergency first responders dealing with an emergency situation, and they need to know, in case it's some kind of inhalation, they need to know what they're dealing with and how then to treat that patient, all right? Okay. So some of the chemistry skills are especially knowing the shapes and structures, the Lewis structures of molecules, and then when we talk about the combustion reactions, how to balance those equations. Okay. All right. So organic basically means that the source is from some kind of a living thing, or a plant, animal. However, like I said, since then the definition has changed in the way, in the sense that you are able to synthesize a lot of the organic compounds in the lab. All right, urea was the first organic compound that was synthesized in the lab, mostly from inorganic uh, compounds. All right, and since then a lot of the drugs, the pharmaceuticals are organic, and like vitamin C, etc., and they are able to be synthesized in a laboratory as well. And the vitamin C that you derive from the fruits, the citrus fruits, and other plants or vegetables uh, behaves exactly similar to the synthetic vitamin C. Okay, so therefore, both of the vitamin C's, the reason that they behave very similarly, whether they are produced outside the body, outside an organic source, or derived from within the organic source. And the reason is because they have something called the functional group. And so the functional group behaves exactly the same. All right. Okay. No matter what that source of the organic compound. Now, because carbon and hydrogen, okay, the polarity difference is so low. Methane, for example, CH4, right? The carbon hydrogen bonds are there is not much of an electronegativity difference. Hydrogen is 2.1, carbon is 2.5, so 0.4. So the carbon hydrogen bonds are non-polar. Therefore, most of the hydrocarbon compounds tend to be non-polar and therefore not soluble in water. Remember, like dissolves like, so something has to be polar to dissolve in water, and hence oil does not dissolve in water. So, an organic compound must contain carbon and hydrogen. In addition, there are other nonmetals that are also found in some of the organic compounds. Oxygen is very common, so is sulfur, nitrogen, phosphorus, or halogen. All right. So, organic compounds are so vast. Most of the things that we either are consuming or using are organic. Okay, so gasoline, medicines, shampoos, you name it, they are all organic compounds. So, as I said, there's millions of these organic compounds, and it's impossible to study them individually. But when they are organized by what is referred to as the functional group, so this is a group of atoms that are bonded in a specific way. Okay, so in that kind of specific bonding, what happens is they have very specific chemical reactions that they undergo. Okay, so we can study all these millions of organic compounds, because if the compounds we're studying have the same functional group, then it's quite likely that their physical chemical properties are going to be similar. So in this way, by organizing them by their functional groups, it becomes easy to study them. All right, so organic compounds are molecular compounds, so they have covalent bonds, all right, bonds formed by sharing. And a lot of the times those bonds are non-polar, and therefore the organic compounds are non-polar. They will not mix in water. And unlike inorganic compounds, the bonds are doesn't take much to break those bonds, so the melting and the boiling points are quite low. All right, inorganic compounds such as NaCl have very high melting points of in the range of 800 degrees, whereas you know very well that alcohols or gasoline, it's easy to burn them, all right? So they're very flammable. They undergo combustion, all right? Combustion is the reaction where they are reacting with oxygen from the air and forming the products carbon dioxide and water, okay? So oil and water don't mix, and so they're insoluble in water because they're non-polar. All right. Inorganic compounds, if you compare side by side sodium chloride and an organic compound like propane. Propane is what we use in for when we are grilling a barbecue. So those propane tanks. And here it's nothing but carbon and hydrogen. There are 3 carbons um, uh, and 8 hydrogens, as you can see. So each carbon, when you write the formula of propane this way, this is called as the structural formula, you can see that each carbon at the end is surrounded by 3 hydrogens, and the carbons in the middle have 2 hydrogens, all right? Okay. So the other thing to draw a conclusion from this is carbon is always forming 4 bonds, all right? 4 covalent bonds, okay? Anyway, so propane, if you compare propane, it burns easily, very low melting and boiling points, whereas sodium chloride, as I said, it takes, even to melt 1 small grain of sodium chloride takes a lot of energy. 801 degrees centigrade is the melting point of sodium chloride, right? So high melting boiling points, okay? The interactions are ionic. It's between the attractions of cations and anions. And of course, because of the fact that they are so highly polar, they're soluble in water, all right? Propane, on the other hand, is going to be insoluble. It's a gas, not very soluble in water. And it's an organic compound, and the bonds are the carbon-hydrogen non-polar bonds, okay? Propane is a fuel. Fuel supplies energy when you burn it, okay? So to compare them side by side, organic, carbon and hydrogen, metals and non-metals for inorganic, they exist as molecules. They exist mostly as ions for inorganic. The bonding is covalent in organic. The bonding is ionic in inorganic. The bonds are non-polar unless you have an oxygen or a nitrogen or sulfur present within the organic compound. The bonds are ionic and therefore very polar for an ionic compound. Melting boiling points are low for organic but high for inorganic. Easy to burn the organic. Salt, doesn't matter if you have table salt next to a flame, nothing is going to happen. Organic compounds are not soluble in water, but inorganic compounds like sodium chloride will be highly soluble in water. Okay. All right. So in the study check, it says identify each characteristic as mostly typical of compounds that are inorganic or organic. High melting point, that would be inorganic. Not soluble in water, organic. Contains carbon and hydrogen, organic. Has the formula MgCl2, metal, non-metal, inorganic. Burns easily in air, and that would be organic. All right, so hydrocarbons, as they are called, can be represented several ways. You can make models, like for methane, carbon surrounded by 4 hydrogens. For covalent bonds, carbon always forms 4 covalent bonds by sharing of its electrons. Each carbon has 4 electrons to share, so each hydrogen brings its 1 electron to share with it, forming the 4 covalent bonds. Okay, the type of shape is a tetrahedral according to the Vesper theory. The bond angle is 109.5 degrees. Okay, and you can either represent it with using models. This is a space filling model, or you can represent it two-dimensionally by drawing it out. And when you write it like this is called as the molecular formula. Okay, this is called as the structural formula. And you can represent it flat like this, 2D, or try to mimic a 3D, sort of like this. Okay, all right, we'll stop here.